So we've established the elegance of backpropagation, but its simplicity comes with two structural liabilities. What are the two major disadvantages we're constantly fighting against?
First, as we noted, it can be slow and inefficient, especially on large, deep networks. This is what drives the need for better optimization algorithms. And second, and this is the classic problem, gradient descent can easily get stuck in local minima. The algorithm only uses local information, the steepness right where it is. So if the initial randomly set weights guide it into a suboptimal valley, it may never escape to find the true global minimum.
That initial weight configuration determines the final performance, which seems like a terrifying lack of control. Let's look at the solutions developed to overcome these pitfalls, starting with momentum.
Momentum is a really intuitive fix to both problems, both the slowness and the local minima. If you think about the gradient descent path as a ball rolling down a bumpy hill, basic gradient descent stops whenever that ball hits a slight dip. Momentum gives that ball inertia, so it keeps it rolling, keeps it rolling. Mathematically, momentum works by adding a percentage alpha of the last movement, delta W at time 2 minus 1, to the current weight update. The current direction of movement isn't just based on the steepness right now, but also on where the algorithm has been consistently moving.
So if the gradients are all pointing in the same general direction,
Momentum builds up and it amplifies the movement.
so it helps us power through those tiny speed bumps that might trick the system into thinking it found a minimum.
Exactly. It uses that accumulated historical velocity to navigate over small, shallow bumps in the error function, which often allows it to find a deeper minimum in significantly fewer steps. The momentum term, alpha, is typically a number like 0.9, representing a strong historical influence.
But there's a catch, right?
There is. The crucial caveat is that momentum, while it's vastly superior to basic gradient descent, still does not guarantee a global minimum. It just improves the odds and the speed of finding a better local solution.